My name is Olga Pawluczyk, and I work for PPO TechTalk. At PPO, we answer, what's in your food? Today, I'm going to talk a little bit about understanding and performance of inspection systems, specifically how that applies to vision systems. I'll also compare a few types of vision systems so that you can better understand what the differences are. Show you a few applications of hyperspectral imaging, and then I'll come back and talk a little bit about vision systems considerations when you're thinking about maybe installing one of those systems in your life. So first, a little bit about performance of inspection systems. One thing to really think about is the terminology that's being used. So consider events which have two definite outcomes. So something is true and something is not true. So for example, having a certain medical condition, or in case of food processing lines, having foreign contamination, or even product quality, a good product or great product compared to all the rest of the product, and things of that nature. What's kind of maybe not sometimes considered is that we can only try to determine reality through measurement. So we actually typically don't know the complete truth about how well our system is performing in inspection, because no measurement is perfect. So somebody might test positive for a medical condition that they actually don't have, or test negative for the same medical condition that they do have. So that really is something to think about, is false positives and true positive rates. And correct detection is really true positive, and that's what typically we can very easily measure and determine. So typical studies for detection and inspection only address the true positive counts, but the actual true and false negative rates are not known. For humans, that's even worse, because not only can't you know what objects have been missed, but you also don't know what false positive rates humans have, because they just don't report it. So when considering automated versus manual inspection methods, it's important to think about how the human brain works and how the human vision system works. So our eyes are exceptional at finding really hard to see and determine objects. So smallest speck of something new, a lot of the times humans can find it. The problem is humans get tired and lose their vigilance. So in literature about human inspection, we see that vigilance of operators drops over time, and it can reach as low as 30–40% in a span as short as 40 minutes of inspection task. This is even further compounded by other human factors, so environment, how well they've been trained, how well they like performing the task, and even things like lighting and temperature in the facility. So although humans are fantastic at finding very weird and novel foreign objects, they're not great at paying attention all the time. And that's different with automated inspection methods, which don't get tired. There is a bit of upkeep, obviously, that each automated method does require, but overall, their performance does not degrade over time, and they can typically work multiple hours a day, 24/7, is not out of question for some of the inspection systems out there in the market. So let's talk a little bit about what it means to detect something. Typically, everybody can find a small piece of something. If it's just presented perfectly well and tuned to a given system, it's very easy to find a small object. However, it's not possible to find that small object 100% of the time. And this is where something called the detection curve comes in. So what is the percentage of time that a given size of object can be found with a given detector? And humans are very good at finding small objects. However, they don't find them 100% of the time, and neither can X-rays, metal detectors, or any vision system out there. Nothing, no technology, and no inspection system is perfect. And the detection is really a combination of the system resolution, pixel size, noise, configuration, the product itself, and algorithms that are being used to tease out the information from a large data set about finding a given product. And this detection curve is really the primary way of comparing different detection systems. And again, just pay attention to the fact that the single smallest object detected does not mean that that's the best performance. Sometimes that object can be found at a fraction of a percent of the time, and then it's not detectable in less great conditions. This detection curve also applies to product grading. So, for example, how often will a great product be classified as great versus not great? The final aspect to consider about any detection system is the false positive rates. And that means that the detection system says that there is something there, that product is rejected, but actually there was no foreign object or poor quality seen, or it was seen, but it wasn't present. And this false positive is really important to understand because it really affects how much of your product is rejected for no reason whatsoever. And obviously that number, if it's several percent, you never want to reject several percent of your production. So let's talk a little bit about vision and detection. So there are many modalities that can be used, from microwave, ultrasound, ultraviolet, and even more complex methodology like magnetic resonance imaging. And all of those excel at some things and are not great at some other things. In food processing, we tend to stick with X-rays and just typical measurement of light. And we do have metal detectors which do measure impedance. But really, these are kind of the basics of imaging in food processing. And how do we look at that? So this is an illustration of a vision system that does hyperspectral imaging, where an entire row of pixels is detected all at the same time, and each pixel has a lot of information attached to it. So in terms of traditional vision, it might have a couple of colors. In multispectral imaging, it will have tens of colors, and in hyperspectral, it will have hundreds and even thousands of colors. What these imaging systems vary in is kind of type of data they gather and what can be learned from the data. So let's talk a little bit more in depth. So here's an example of chicken nuggets, which have a couple of foreign objects placed on them. And in a standard vision system, just like our eyes, we see 3 colors differentiation, and we can pick up some of these foreign objects better than others. But really what we're looking for is brightness and contrast of color, and really, very different colors, very different brightness is much more easily detected than others. In multispectral systems, we now see not just 3 colors like a camera, but we see 10, 30 colors at the same time. These systems are really developed to differentiate things that are well known. So for example, nuts versus everything that's not a nut would be a very good example of a multispectral system. Also, if you want to find a very specific type of plastic, it is again quite useful to use a multispectral system. However, these systems are very specific to a given color and amount of information available and tend to be not so flexible. So the last methodology that can be used is hyperspectral, and I'll talk a little bit more about that, but really it's using science of spectroscopy to see how light interacts with matter. Different chemical bonds will absorb the light, and what we see back is really information about chemistry of product and food. So this is an example of that, where every pixel in this image contains hundreds of wavelengths of information, and the differentiation between these spectral curves gives us now idea about chemistry of the food. So you can see how a foreign object has a very different wavelength pattern than meat, which has a much closer to each other types of spectral information. So comparing these methods, a typical vision system really provides a quick methodology of looking at contrast and brightness. Multispectral imaging is a little bit more flexible, which allows us to see basic chemical information. And hyperspectral imaging really provides so much information that not only can we determine things that we've seen before, but over time this system can learn new chemical signatures and start looking at food in novel ways after it's been installed. So here is an image of detection of bone in chicken. And what I wanted to bring your attention to is the fact that we're not looking here at density, but we're actually seeing different chemical composition of bone versus meat. So, connective tissues and fat will look different than bone, even if visually it's quite similar coloration and so forth. Another example is looking for a very tiny speck of rubber on top of matrix of bacon bits. Again, something that visually it would be almost impossible to see is very well detected and identified as a specific chemistry using hyperspectral imaging. So we can see here something that would be almost impossible for a naked eye to see is seen, detected, and identified as a specific type of rubber. One question that's asked about vision systems is obviously the fact that they're vision, so they don't penetrate into product. And that's true to most vision systems, although infrared light does penetrate into product, it does get things quite blurry. But how this is solved very often is by flipping the product. So here is an example of pork trim with a couple of foreign objects visible, but we don't know if the meat might not be obscuring something else. We actually agitate and flip the product, and here you are, you can see additional foreign objects. So most vision systems allow you to somehow look at both sides or multiple sides of the product at the same time. Typically, several vision heads are attached to some sort of agitator or flipper. Finally, the quite interesting aspect of hyperspectral imaging is something like quality determination, where it's possible to attach chemical information of the spectrum and correlate it to quality measures. So for example, here we were able to grade pork loins for their water holding capacity and their ability to be tender. The same system can not only find foreign objects and quality, but can also measure chemistry and composition measurement. So again, one system can do all three things, and here is an example of measuring fat within proportion. And finally, some complex states like woodiness of chicken breasts can be determined with a hyperspectral system. And again, we can sort lower quality or woody breast out of the production line so that that premium product reaches the customer and lower grade product can be processed elsewhere, thus saving money. So finally, as I'm finishing this presentation, I just wanted to bring it all back together. When you're looking at new inspection system, whether it's vision system, X-ray, metal detector, or something new, it's really important to understand that balance between detection rates and false positive rates. And understanding that oftentimes, the smallest object found by the system does not mean that that's actually going to be the performance. So it's really important to understand what your needs are and how a system will operate in your factory, in your production line. Thank you so much, and I hope that this was an informative talk. If you have any questions, please feel free to contact me. Thank you, and have a great day.